The next talk is given by Michaut from the Institut de Physique Volcanoes. And we add another phase and a lot more excitement.
Thank you very much for the invitation. So I'm going to talk about melt extraction at subducting plate boundaries. So another plate boundaries. So first the settings, what happens at plate boundaries, that partial melt is formed by dehydration of the subducting plate. So the mantle above gets enriched in water, and this causes its partial melt. The melt is enriched in water and in silica relatively to the surrounding mantle, and it ascends up to the base of the crust by porous flow or channelized flow, you tell me. And at this point, at the base of the crust, it faces a low-density crust, a complex crust, which is also probably stratified in composition in between a lower crust, which is probably more mafic, and an upper crust, which contains more silica. So in order to understand melt extraction from the mantle and at the surface at these subducting plate boundaries, we need to well characterize the transfer function that is associated with this filter, the continental crust. And you will see in the following that this has a lot to do with trying to understand melt segregation and multi-phase flow. So in the following, I will try to start from observation and so describe you the observation that we have at silicic volcanoes and try to emphasize where two-phase flow are important for our understanding of melt extraction. So since the 80s, we have largely, the monitoring of silicic volcanoes have largely been developed around the world because these volcanoes are very dangerous. And so we have learned a lot of things from the records of the seismic activity, the deformation that is monitored and using tip meters or even GPS network, and also from the gas flux that is emitted at a given volcano. So these observations have led to, I think, two main discoveries at these silicic volcanoes concerning melt extraction. So the first one is that no liquid chambers have been observed even below very active volcanoes. And the second one is that silicic volcanoes present cyclic behavior and cyclic activity. So this came as a good surprise and was even used for risk assessment at Montserrat, where this picture has been taken at the observatory. So since the years 1996. Yeah, so I'm gonna comment about those two main observations, and I'm gonna take most of my example will be taken from the volcano, the Soufrière Hills, Montserrat, because this is one of the best studied volcanoes in terms of geophysical data and experiments. So no liquid magma chambers below volcano, despite many seismic experiments and observation. We only find a partial melt below volcano. This is an example at the Soufrière Hills, where an active seismic tomography experiment has been conducted, and we find partial melt at 8 kilometer depth with a melt fraction of only 10 to 12% of melt. However, we know that liquid reservoirs exist since large eruptions occur at these silicic volcanoes, caldera form. And we also know that these volcanoes are long-lived systems. They are active for hundreds of thousands of years. And even geochronology tells us that crystals remain in the reservoirs for hundreds of thousands of years, up to 1 million years. So taken together, all these observations suggested that magma chambers are not liquid chambers that cools down convectively and are not formed by diaperic ascent of melt within the crust, but are instead formed by accumulation of small magma volume within the crust. So in the late 2000, we started to develop static thermal models of magma chamber formation, where injections are placed instantaneously in the crust and progressively heats up the crust up to the point where the solidus is reached and where you can form a mush and where you can have liquid in the crust. So this is the critical time needed for the formation of, for the survival of melt in the crust as a function of the rate of injection, the vertical rate of injection. You can see that it decreases with the rate of injection and it reaches hundreds of thousands of years for a rate of injection of about 10 millimeter per year. So this is when we assume equilibrium crystallization in the magma when it arrives and is emplaced in the crust. So what you can see here is that the temperature in this system progressively increases as melt is being emplaced in the crust, and it reaches a quasi-steady state, which is marked by a maximum temperature, and this steady state occurs just below because the heat injected with an injection is equilibrated by heat conducted away, by heat lost by conduction. So there is a critical rate below which you cannot form liquid in the crust because the solidus temperature is not reached and the heat is lost by conduction. And unfortunately, so this critical rate depends on the depth of intrusion. Here it's not a ZS. And it's 10 millimeter per year for a depth of injection of 5 kilometers. It's 2 millimeter per year for a depth of injection of 25 kilometers. And unfortunately, it's at the limit of observed geological rate of injection deduced from the lifetimes of plutons and from the volume of plutons. So this suggested that magma chambers in the continental crust were formed during period of high transient input rates from the mantle. So do we need transient higher input rate from the mantle to form a magma chamber in the crust? Maybe not. With my PhD advisor, Claude Jopard, so this dates back from my PhD, we question the assumption of equilibrium crystallization. Indeed, most of the intrusion that we see in the crust, such as seals and dikes, are 1 meter to a few meters thick. And for such thin intrusion, the timescale for solidification by conduction is less than the timescale for crystallization. So that means that this thin intrusion solidified in the crust, in a cold crust, keeping a large proportion of glass and keeping their latent heat. So these are two temperature evolution as a function of time for the same rate of intrusion, but for thin intrusion and thick intrusion in dashed line. So in the case of thin intrusion, the latent heat is not released. So the evolution of the temperature is slower than in the case of equilibrium crystallization. But at some point, there is enough heat in the system to reactivate the kinetics of crystallization. So this is a typical function for the kinetics of crystallization as a function of undercooling, the temperature below the solidus temperature. What you can see is that if you start from low temperature and you increase the temperature, the latent heat that is released exerts a positive feedback loop on crystallization, and hence the latent heat is released in a catastrophic thermal event. So in about 200 to 300 years, here we have an increase in temperature of about 300 degrees that leads to the formation of a mush. So we have liquid, but in the form of a mush. So large volume of liquid can be formed that way. So the time scale for the formation of a magma chamber is about the same as in the equilibrium scenario, but in that case, since the latent heat is released in a short period of time, you can even form a magma chamber for low rate of injection. So unfortunately, this model did not receive much attention at the time in 2006-2010, and was criticized mostly because it requires quite a lot of glassy material being stored in the crust. So petrologists thought that it was not possible to have such a large amount of glass at depth. So now a new kind of model are being proposed by so the first model at equilibrium crystallization was proposed by Katrina Nen and Steve Sparks in Bristol, and they are now working in collaboration with people in University College of London, Solano and Jackson, where here phase segregation is allowed. So you still build your magma chamber by successive magma input that progressively heats up the crust, but here the model is dynamic and allows for phase segregation. So the authors solve for the two-phase equation, including mass, momentum, but also heat equation with a phase diagram. So as injection are being underplated below the reservoir, they progressively heats up the crust. They cool down and heats up the surrounding material. When an injection occurs at the base, it forms a porous wave that ascends through the system and that reacts and equilibrates with the surrounding material. So what is interesting here is that this porous wave progressively leaves behind a mafic residue. So in the end, this model can explain the differentiation of a magma reservoir with a mafic reservoir at the base and a more silicic reservoir at the top. Another positive point for this model is that you can form a liquid reservoir even at very low rate of injection of the order of observed geological rate, because this reservoir forms at the top is differentiated, so it has a lower solidus temperature and is thus can thus form at a lower rate of injection. The temperature is low enough to be sustained by a low rate of injection. You observe also that this reservoir is quite rich in melt at the top of the magma chamber. So in the end, these kinds of model of mushy reservoir where you allow for progressive magma input and progressive segregation of phase can form differentiated reservoir with mafic residue at the bottom, silicic composition at the top. What is not accounted for here is that this melt is rich, or the magma that comes at the base is rich in water, and as it goes up and decompresses, it progressively releases its gas. So there is another phase that has its importance here. It's the gas phase. So in the end, what I want to tell you here is that a magma chamber is a reservoir of mush that is extended over several, up to more than 10 kilometers in the crust, and that is composed of 3 different phases with very different properties. And my question is how those 3 different phases can interact and segregate to explain the variabilities in melt extraction observed at the surface. So now I'm going to switch to the other kind of observation, which is that the activity at silicic volcanoes seems cyclic and periodic. You have very different periodicities that have been observed, going from the hour to several kiloyears, and these examples are taken from the Soufrière Hills volcano in Montserrat. So I'm going to shortly review all these periodicities. So very long periodicities are recorded in the eruptive product. So at the Soufrière Hills, Montserrat, we observe that large volume eruptions of compositionally indistinguishable andesite are emitted every 6 to 4 kiloyears at 24, 18, 12, 6, and 2 kiloyears. So you have a nice cyclicity here. Another periodicity that is observed at silicic volcanoes in the eruptive product is a periodicity of a few tens of years, where periods of activity that last a few years alternate with periods of dormance that last about 30 years. So for instance, you see period of activity, historical period of activity, in 1896, 1933, 1966, 1996, and 2006 at Montserrat again. So the multi-year periodicity is also observed in the geophysical signal. So in the seismicity and in the inflation and deflation of the edifice. What you see is that during period of quiescence, the edifice inflates and the seismicity is very low. But during period of activity, the volcano deflates, and this is associated with very large seismicity. So what is interesting in terms of three phases is that the gas phase do not seem to correlate with this cyclicity at this multi-year period. The gas, the SO2 emitted at the volcano is quite steady over a multi-year time scale. So this seems to suggest that the gas is decorrelated from the melt over these time scales. Another important observation is that since 1995, the sulfur that has been emitted at Montserrat is much larger than what could have been present in the total volume of erupted andesite. So this observation suggests that the SO2 that is emitted during a period of activity was coming or is coming from underplated basalt that was accumulated much before the eruption. So this suggested the author, Christopher and collaborator, so the authors suggested that this was because during a period of unrest, the system, the extensive system, was suddenly becoming contiguous and allowing for gas flux from the bottom to the surface. Then you observe shorter periodicities. Here in Montserrat, you observe a periodicity of 50 days in the extrusion rate that is observed also in the seismicity and in the degassing record. This 50-day cycle has been explained by Melnick and Sparks in 1999 by the nonlinear dynamics of lava dome extrusion. So this short time scale is explained by a process that occurs in the conduit, and it occurs because at some point, because the flow is slow enough, cooling allows for a large crystallization in the ascending magma, and a rheological transition can be reached where the viscosity suddenly jumps. So in fact, what you have is that for a given overpressure in the chamber, you can have different solutions at low and high discharge rate, depending if the rheological transition is reached or not in the conduit. Finally, and this is what I'm going to talk more in the next slide, at Montserrat and also at different silicic volcanoes around the world, we observe the cyclicities that is of several hours. So this cyclicity is observed in the seismic record. So this is, for instance, at Mont Pinatubo in 1996, where you can see that the seismicity, the number of seismic events, increases and decreases with a period that is quite stable of 10 hours here. So in between two maximum, it's about 10 hours. And this was particularly stable at Mont Pinatubo at that time. At Montserrat, this periodicity in the seismic number of seismic events and seismicity is accompanied by cyclic inflation and deflation of the edifice. So this is recorded by tiltmeters. What has been observed also in Montserrat is that the degassing also fluctuates with the same periodicity. And at the cycle peak, it was observed major eruptive events such as pyroclastic flows, volcanic explosions, or even rapid dome growth. And at all these volcanoes, the periodicity varies from several hours to a maximum of about a day. So at all these volcanoes, Mont Pinatubo and Montserrat, and also at Mont Sakurajima in Japan, we observe that the geophysical signal, the tilt and seismic amplitude, decrease rapidly with distance from the summit, suggesting that this low periodicity originate within the conduit also. At these volcanoes, you observe also that the periods vary from a few hours to a few days, but this is regardless of the volcano around the world, Mont Pinatubo, Montserrat, or even Sakurajima. And the signal persisted even despite the destruction of the edifice. So this suggests that the signal does not seem to be related to the geometry of the conduit or of the edifice. So a popular model was proposed to explain this periodicity of a few hours and consists of a stick-slip behavior of a stiffened plug, rheologically stiffened plug, along the conduit wall. So below that plug, gas is being released and accumulates, and this led to large overpressure, which at some point can lead to the can overcome the static friction here and lead to the slipping of the plug. The pressure then release, and at some point it's so enough for the plug to stick again. So this model is nice because it explains rapid variation in extrusion rate and seismic swarms, but in the other hand, it depends on the conduit geometry and on the plug geometry. And also, when you have an explosion at the surface, the plug is destroyed, and you need to explain its regeneration in only a few hours to explain the occurrence of a new cycle. For instance, at Montserrat, 75 explosions has been observed that succeeded each other with a period of about 10 hours. So you must explain the regeneration of this plug in the context of this model in only a few hours. So with my colleague Yannick Ricard, Dave Bercovici, and Steve Sparks, we propose that these cyclicity were coming from competition between two processes that occurs in the conduit because of the presence of two phases, the presence of a gas phase and the presence of the melt, of course. So the melt compaction, magma compaction, occurs in the magma over a length scale, which is the square root of the viscosity of the magma divided by the resistance to percolation of gas in this supposedly permeable magma. And for very viscous magma, such as in silicic volcanoes, the viscosity can reach about 10 to the 8 to 10 to the 11 Pascal second in the conduit, and in this case, this leads to a compaction length of 1 to 15 meters. So it's not much, but you will see that it can be important for silicic volcanoes. So this compaction in the mixture of gas and magma occurs by gas expel, gas transport, but also by compression because the gas is a compressible phase. The other competing mechanism is that the mixture is ascending toward the surface, and in that case the gas sees pressure that are decreasing and the gas expands. So you have compaction that leads to a decrease in the gas fraction and gas expansion that leads to an increase in the gas fraction. So two competing mechanisms. So we know that in a two-phase flow the fluid is expelled through the mixture, through the mixture by porous waves that are stable. And here we were wondering, in the case of a compressible gas, if the compressibility of the gas could lead to an unstable wave, and if this could lead to a preferred wavelength for this instability. So we developed the well-known two-phase equation for the conservation of magma and gas mixture with a compressible gas, and the momentum equation, so the Darcy flow of gas and the compaction of the magma. And we did a linear stability analysis of this equation. So our zero-order background state is a constant gas fraction. So this can be criticized because the gas fraction increases in a volcanic conduit as gas is being exhaled from the melt and as gas decompress, but it's at least true locally. Then we assume that the perturbation in gas fraction and gas density and velocity of the melt and gas are sinusoidal perturbation. So we put that in our equation and we end up with a dispersion equation that relates the wave number, k, which is the inverse of the wavelength, with the wave velocity that can be complex. And if the wave velocity has an imaginary part, then we can have an unstable wave. So this quadratic equation is a function of two dimensionless numbers that control the pressure and the density difference between the two phases, but only the parameter beta play a role in this equation. And this quadratic equation shows two solutions. One is a solution that is propagating, that shows wave propagating upward and decaying, and the other one shows a solution where the wave can be unstable. So this is a growth rate, the imaginary part of the velocity as a function of the wavelength of the perturbation. So first, when you don't take into account the compressible effect, the compressible gas, when the gas is incompressible, you have a stable solitary wave with a growth rate equal to 0, and this is what we find in the linear stability analysis. When you neglect compaction, all the wavelengths are stable, all the wavelengths are unstable because gas expansion is allowed. But when you account for both gas expansion and magma compaction, you observe this kind of growth rate as a function of the wavelength, where small wavelengths decay because compaction compresses the gas and is large enough to compress the gas. Large wavelengths are allowed to grow by gas expansion, and there is a dominant wavelength where the growth rate is maximum because a very large wave just allows for gas escape to the surface. So we also developed numerical solution to the nonlinear equation, and the numerical solution confirm this stability analysis. So this is the conduit going from 0 to 5 kilometers. It's the excess gas fraction in excess of the background gas content. The A case is for the case where the gas is incompressible and the B case is for the case where the gas is compressible. So we allow for a random fluctuation of the gas content at the base of the conduit, and you can see that when the gas is incompressible, these perturbations are transmitted up to the top of the conduit with no growth or no decay. It's the classical porous waves, stable solitary waves. In the case where the gas is compressible, then you can see that quite quickly a wavelength is selected within the conduit and grow very slowly, but it grows. So here is again the numerical solution, the background gas fraction, and the fluctuation of the gas content around this background gas fraction. These gas fluctuations are associated with gas pressure fluctuation in the conduit. And what you can see is that the preferred wavelength is 200 to 300 times the compaction length. And the linear stability analysis predicts that for a wide range of parameters, particular gas density or a wide range of the value of beta, this dominant wavelength is between 100 times the compaction length and 1000 times the compaction length. For a compaction length of 1 to 15 meters, this gives a wavelength between two gas poles of 100 to 1500 meters. So these waves of gas travel in the magma, within the magma, with the Darcy velocity. And the Darcy velocity is much smaller than the ascent rate at these silicic volcanoes. So in the end, the periodic arrival of a gas pulse at the surface is just the wavelength divided by the ascent rate. And for characteristic ascent rate between 10 and 15 meter per hour at Montserrat, this gives a period of a few hours to a few days, as observed. So in the end, the competition between magma compaction and gas expansion in silicic volcanic conduit led to growing oscillation of the gas fraction with a dominant wavelength that is between 100 and 1500 meters. At the surface, at the vent, we would see with the arrival of a gas pulse, periodic inflation and deflation of the edifice, periodic degassing, and periodic explosion or periodic pyroclastic flows. A prediction of this model is that the periodicity is a function of the compaction length, and so it slowly varies with the magma viscosity. So it slowly increases with the magma viscosity, and this is what we observe in Montserrat. In January 1997, for instance, the periodicity was the shortest that has been recorded, between 6 and 8 hours. And at that time, the lobe extruded and shows the most fluid behavior, was very fluid. On the contrary, in May 1997, the periodicity was the largest recorded. It was more than 20 hours. And at that time, a vertical spine erupted, characterized by a very large viscosity. So I'm going to end my talk here. I hope I convince you that two-phase flows is critical, and three-phase flows as well is critical to our understanding of melt extraction at silicic volcanoes, in particular because magma chambers are in the form of a mush. So both magma and crystal segregation is important to understand the stratification of this crust, and magma and gas separation is also very important to understand melt extraction and the periodicities that we observe at silicic volcano. Thank you.
Great. got 10 minutes for questions. Let's start here and then we'll go to the back.
What, do you have any comments about the longer period oscillations? I mean, this explains the 10-hour type, but what about the ones that are years?
Of kilo years or years? No, I leave that to the community. I think that they are still to understand. There is no real mechanism. Maybe it's just the kilo year period is associated with some rejuvenation of this mesh and with higher input rates from the mantle, or some other processes linked to phase separation and phase segregation. So there is still a lot to do to understand these periodicities.
Toby in the back?
Yeah, I was just wondering if you could comment a little bit more on the physics of gas percolating through what looks to be quite a stiff magma, because if it forms like a dome or a spine extrusion on top, it must be quite hard. And I have troubles imagining what the physics look like. I mean, in a very runny magma, you'd imagine little bubbles coming through, but in a stickier magma, how does it actually physically work, the percolation of gas through the magma?
So here you have to understand that even within the conduit that is only a few kilometers or up to 10 kilometers thick, the property of the magma largely evolves as you go up. So the very, very stiff magma will be obtained at the surface, but at the base you still have quite viscous magma. So in fact the viscosity will largely change as you decrease the gas fraction, as gas is being exsolved and as crystals are segregated. So still you can have gas segregation from the magma from the bottom up to a certain level in the conduit. And indeed at the surface you might have a very stiffened, biologically compacted layer that indeed can plug up the conduit.
But then you would need fracture to get to that last bit, or you could, if you get fracture, essentially you could get explosion, right?
Yeah, to destroy the plug you need fracture and maybe fragmentation and yeah.
Right, thank you.
Jerome?
So for your plug, you've done a stability analysis which is assumed that you get a uniform flow which may vary in amplitude with time. Do you think that, is there any reason to suspect that you'll always get a uniform flow, or might you have instabilities that give you fingers going up one side of the conduit or that sort of thing?
So I did not quite get your question. It's related to which...
So you did a stability analysis which asked if you got traveling waves.
Yeah.
Your traveling waves ever have any azimuthal instability?
Okay, this is something we are currently working on, trying to see if indeed gas could migrate towards the conduit, in particular because in a conduit you have a Poiseuille flow that is sheared, and that could lead to some gas expelled toward the conduit, and so this is something we are currently working on, and it takes time.
Yep.
So, if I understand well, there's a transition between two phases that would be the magma and the mantle and the crystals, to a part where the two main phases are the magma and the gas.
Yeah.
So you can treat one and treat the other, but for the region where you have three phases, is this region negligible, or what would be the thickness of this region, and can you elaborate on the role of this?
So this layer will probably evolve with time, as you probably understand from the talk. It's probably transient. The period where you have a relatively large liquid volume in the mesh and large gas volume. So probably the effect of the three phases are important there. To extract in particular the liquid from the mesh. This is people have worked on that and have shown that the gas is important in triggering the separation of the liquid from the mesh. But there are a lot of things to do there.
So if I could ask a question. Yeah. You've looked at the mechanics. I guess, from slightly naive perspective, energy is moving around in the system as well, and when you exhaust gas or condense gas, I suppose you have also compression and expansion of gas. Are these phase changes and volume changes enough to significantly affect temperatures, and if so, mechanical properties of the conduit?
So yeah, so during the ascent of the mixture within the conduit, you have indeed crystallization. It's important for this is also important to understand the variabilities of metal extraction over a period of a week. And this crystallization leads to latent heat release that can. So what happens is that. What happens is that as you go up, the gas is being exhausted, so the magma becomes drier, so the liquidus temperature becomes higher, which triggers crystallization. So gas exsolution would decrease the temperature, so the effect of gas exsolution on the energy would lead to a decrease in temperature, while crystallization would lead to an increase in temperature. Both of these effects compensate, but the effect of latent heat release is a bit higher. So over the conduit length, you can have an increase in temperature of a few tens of Kelvin, for instance.
Probably not enough to affect the mechanical properties in an influence.
Yeah, the mechanical properties of the magma is much more linked to the effect of gas solution leading to a dry magma and to a much more viscous magma. So it's not the temperature that will change the magma properties, it's more the gas solution, but not the energy effect.
Thanks. I guess could the next speaker come up, and we have time for maybe one more question.
So you're describing percolation of bubbles was that Darcy's law that you had?
Yeah, we use a permeable magma in that case, but we also developed the model for particle suspension, and we obtained the same kind of behavior.
Same kind of behavior. And what were your peak porosities?
Peak porosity is a gas fraction, so I can show you. Sorry. So they go. So we did the simulation up to 70% of gas. Here.
70%. So
Yeah, because after
you run
that
into
you have fragmentation, and the gas becomes the dominant phase.
So do you run into the same problem that was discussed about the disaggregation limit?
So after fragmentation, you have an explosion, basically.
All right. If there are no more questions, let's thank Chloe again.
Thank you.